Okay, we continue this discussion of measurable functions and their integrals. So again, consider a sequence of non-negative functions, fk, they're defined on the measurable set E, they are taking non-negative values. And suppose the sequence is non-decreasing at every point. So that means for every point, fk of x is less than or equal to fk plus 1 of x. And we also know that since this sequence is monotone, suppose the limit of this sequence is defined to be fx, then we know that the Bipolar theorem says that the limit of the integral of the sequence is equal to the integral of the limit, which is this f. Okay, so that means you can switch the limit and the integration. Okay, this is the very important theorem that is a foundation of many other theorems later. The key here is that if you can have a non-decreasing sequence that convert to a function f, then the integral of this sequence will also convert to the integral of this limit function. Okay, so let's see how to prove this. Okay, first of all, we know that the fk is non-decreasing. So in other words, the fk is non-decreasing and converges to f. And we know that the integral of this fk is also non-decreasing. Okay? So it's also non-decreasing. And this is just a sequence of numbers. So they will either convert to some number or they go to infinity. Right? So you know that's just a monotone sequence of numbers. And also, we know that the limit of this sequence, the integral of this sequence, is also less than or equal to the integral of f. The reason is that fk is less than or equal to f. The integral of fk is less than or equal to the integral of f. And you take the limit, it's still less than or equal to the integral of f. Okay, so now the key is that how do we show that this is actually equality instead of inequality? Okay, to show this, let's first consider a approximation of the function f using a simple function. So for any simple function h less than or equal to f, and any, let's say, any number between 0 and 1, we'll define this set ek to be the set of points where the fk of x is bigger than or equal to c times h of x. Okay, so this is the set of points in E, and apparently, since fk goes to converge to f, and hx is less than or equal to f, so hx is less than or equal to f of x, and so the c of c times hx is also less than or equal to f of x, because c is between 0 and 1, and assuming that everything is greater than or equal to 0 now, because f is greater than or equal to 0, so the h is non-negative simple functions as well. And because it's fk, so that means this, if this hx is positive, then c times hx will be, so there also will be c times hx here. Okay, I'm just evaluating their checking their values on the real line. And this fx is less than equal to, is greater than equal to hk, so it must be on the right side of hk or is equal to hk. The point is that if hkx is greater than 0, then since fk is going to f, is converging to f, so that means it will be bigger than c times hx after a certain k. Right? So we know that the point. Let me rewrite it here. We know that this ek apparently is increasing or is non-decreasing because the sequence fk is non-decreasing. So you get potentially bigger. If k is larger, then potentially you'll get more points that's bigger than or equal to c times hk, c times h of x, and also this will eventually go to the set E. The reason is for every x, we can, as I showed here, for every x, you can see that either f of x equals to 0. Then in this case, hx must be equal to 0. And then all the fk of x must be equal to 0 as well. Then we don't need to do anything. But if fx is bigger than 0, then we know that you choose the simple function. This hx will be equal to 0 or greater than 0. Doesn't matter, but it must be less than or equal to f of x. So it's either equal to 0 or it's bigger than 0. Let's say that if it's equal to 0, then apparently the fk of x goes to f. So that means starting from some k, the fk of x will be bigger than 0, which will be bigger than h of x, and is also bigger than c times h of x. Right? So that means x is in the set of ek. Or if hx is bigger than 0, then that would be the case I just mentioned. So this is 0, this is hx. This fx will be either here or on the right side. But if you take it multiply the hx by c, then the c times hx is here. And your f will be here or even bigger. So that means the fk will eventually become bigger than c times hk, c times h of x. Right? This will be fkx. Okay, that means x will be inside ek for some k. Okay, so for any x, we can show that x will be in ek for some k. So that means the ek will eventually grow to the set E. Right? So that's the argument here. And based on this, we can show the following inequalities. Let's look at the limit of the integrals. Remember, eventually we want to show that this limit is equal to the integral of f over E. Okay, sorry, it should be, yeah. Okay, so first of all, I know that this is fk is non-negative. So when I take the integral of fk over the entire E, will be bigger than what I take for the integral over a smaller set ek, right? Because ek is a subset of E. And over this set ek, I know this function fk is bigger than or equal to c times h. So this means this is bigger than or equal to limit of this ek and c times h. Right? So and c is a constant, so I can move it outside. So it will be just the c times the limit of h. The k is going to infinity. Right? And we know that this is going to be greater than or equal to, this is just going to be c times the integral, so this is the ek, sorry. The integral of, because h is non-negative, and take the integral of the ek, and the ek is a non-decreasing set. So we know that the limit of this is just the integral of over the entire set E, right? This is the one of the theorems we proved before. Okay, this is because h is non-negative, and this ek is growing, is non-decreasing, and it grows to the set E. So that's why this is true. Okay, and once we have this, we can see that the integral, the limit of the integral of fk over E is bigger than this for any simple function h. Okay, and this c is arbitrary between 0 and 1. So that also means by letting c going to 1, we know the limit of fk over e must be bigger than or equal to the integral of h. Okay, so now we are almost reached to the conclusion here. The reason is that we know this integral is defined to be the supremum of the integrals of simple non-negative functions that are lower than or smaller than or equal to f itself. I recall the definition. This is defined to be the supremum of the integral of simple functions, non-negative simple functions, where this h is simple and the h is less than or equal to f. Right? Now we show that this is true for every of such h. So if we take the supremum of the right hand side, we can see that the limit of the integral of fk is also greater than integral of f, because this is just the supremum of this value. But we need to show that every one of this is less than or equal to is boundable by that. So that's why this is true. So now we show this direction as well. Okay, and combining these two results, we can claim that these two limits are the same. Okay. So there's a remark about this. What if we have a sequence of decreasing functions? So suppose we have fk decreasing to f, then can we make the same conclusion? And it's still true if the first integral or the first f1 or some of those fk's has a finite limit, has a finite integral. Okay, so if this is a decreasing to f and without loss of generality, if this integral of f1, but it could be, as I said, it could be any of those fk's, is a finite number, then, oh, by the way, this f must be non-negative as well. It doesn't have to be non-negative because we are going to subtract the f1 later on. Then this integral, the limit of this fk is still equal to, it's the same conclusion as before, it will be still this. And the proof is very easy. The proof is just to say we can define this new sequence gk to be the f1 minus fk. Okay, and in this case, we can see that gk will converge to f1 minus f. Okay, a non-decreasing sequence. And apparently this gk is greater than or equal to 0 because the sequence is decreasing. So the gk is non-negative and it's increasing to the function f1 minus f. So according to the previous theorem, we can show that the limit of the integral of gk is equal to the integral of the limit, which is the limit of the gk, which is the limit is f1 minus f. So it's just f1 minus f. And on this side, this is just the limit of f1 minus minus fk. But since f1 is integrable, so that's why we can pull this constant out and just get this. Okay, and on the right hand side, this is just the integral of f1 minus the integral of f. So now you can cancel the integral of f1 on both sides. And so we show that this is equal to this. So if we cancel out this term and we put negative sign on both sides, and we will still have this equals this. Okay, so that's for the decreasing case. So the reason why we need this to be finite is because it could be similar as before. The integral of each one is infinite. For example, the fk is the integral, for example, the integral from k to positive infinity is equal to 1 from k to positive infinity, and 0 if x is less than or equal to k. And in this case, the sequence is still decreasing, and it's decreasing, it's pointwise converging to 0, but the integral of each one is equal to infinity, and that's not equal to the integral of 0. Okay, so that's just to eliminate that case. Okay, so now we list several properties of the integrals of general non-negative functions. So they are actually all within expectation, and they can also be proved very easily. So the first one is the integral for general non-negative functions is a linear operation. Okay, so suppose we have two non-negative functions. And any two coefficients greater than or equal to 0, then the integral of their linear combination is equal to the linear combination of their integrals. Okay, it's totally within expectation, and it's obviously true for non-negative simple functions, which is one we proved before. And now we can prove this for general non-negative functions. And the proof is just based on the fact that each of these non-negative functions can be approximated by a sequence of non-decreasing simple functions. So since we know that there exists a sequence of non-negative functions such that fk goes to f and gk goes to g, we know that the sum of them will also go to the sum of their limit, right? So this sequence of functions, fk plus gk, is going to converge to the sum of f and g. Okay, so therefore, we look at their integral, just taking the sum now, assuming that alpha and beta are constants, are just equal to 1. If it's not equal to 1, it's trivial, as we will show soon later. So the sum of this f and g, according to the theorem, the Bipolar, we know that this is just equal to the limit of this, right? And each one of them is integrable, so I can separate this. Each one is non-negative and a simple function, so I can consider their integral, and then they're taking the integral of their limits of their taking the limit of their integrals. And I know that for each one of them, again by the Bipolar theorem, we know this is just equal to the integral of f, and this is just the integral of g. Okay, so this means that the function is linear. The integral is linear in terms of the integrand f and g, and we can easily show it's trivial to show that if we have a function f, and we take the integral of alpha times f, that's equal to the alpha times the integral of f. Okay, you can easily show this. Again, using the Bipolar if you like, and this is true for any alpha greater than or equal to 0. Okay, so we're combining this result, and this is linear in terms of that for any these functions. You can see that we multiply alpha and beta here, you just have alpha and beta here, and you can move this alpha and beta outside of the integral, and that will prove the general result here. Okay. So now let's look at one example. So suppose we have a function, two functions f and g. They're both non-negative measurable functions, and the two functions agree almost everywhere. Then their integral must be the same as well. Okay. Actually, it can be easily shown that since the integral of f can be written over as the integral of two parts, the e1 plus the integral of f on e2, where this e1 is defined to be the set where the function f and g are equal. So it's the set of points where fx equals to g of x. Okay, we know that sometimes I just usually write this as f equals to g. So that's for e1, and e2 will be just the complement of e1. And these two are both measurable sets because f and g are measurable functions. By the way, all the functions that we're considering over here will be measurable. Otherwise, there's no actual definition for approximating them using simple functions. And no, we don't have anything, any theory about those kind of functions. So the f, we always require the functions f and g, or any function we see in this chapter to be measurable. Okay, we don't consider non-measurable functions. And also the sets, the starting, the whole set E were considered to be measurable sets as well. Okay, so now we can consider that. And then apparently here, the integral of E over E1 is just the E1 integral of G over E1 because f and G are the same over the set of E1. And over the set of E2, it's a set of measure 0. So we know that in this case, the second term is just 0. It doesn't change anything. And similarly, if you change it to function f to g, it still doesn't make a difference to the integral since the set E2 has a measure 0. Right? The E2 has a measure 0. So, and this is just the integral of g. Okay. So that's a really trivial result. But it just says that if the two functions are equal almost everywhere, then their functions, their integrals will be the same. Okay, so now let's consider a generalization or extension of the Bipolar theorem, which says that if we have a sequence of or series of non-negative functions, then the integral of the series is equal to the series of integrals. So suppose we have a sequence of non-negative measurable functions, then we can show that the integral of the series, which is defined to be that, right? So that means for each x, the value is the sum, the infinite sum of this fk's. So it will be equal to the integral of fk, the series of these integrals. Okay, so here this is for each point is a sequence of numbers, and we're taking the integral of such a function because it's a function defined inside, and that's equal to the series of these numbers because each one of this is just a scalar, it's a non-negative number. Okay, so proof is pretty simple as you can imagine that we just need to define the partial sum as our function as a measurable function, and then this partial sum will be non-decreasing, and then we can apply the Bipolar theorem. So we can define this sk to be the partial sum, so I from 1 to k of f(i)x. Okay, and then we can also define the infinite sum, which is just the series. Okay, apparently this S K X is non-decreasing because each Fi is non-negative. So we were adding up non-negative values. So this Fk will be non-decreasing and is converging to Sx, 0.1, right? So by applying the Bipolar theorem, we know that this is just the limit of Sk will be just equal to the integral of S. Okay, so on the left-hand side, this Sk, just focus on everything inside the limit. This Sk is this partial sum. And for the partial sum, this becomes just a partial sum from I from 1 to k. But this is just a finite number of functions taking the sum, and according to the theorem before, this integral is linear. So that means this limit inside the limit is just the integral of this partial sum, which is the partial sum of the limit as well. So I from 1 to k, the integral of the fi x, right? And this is just the limit. It's just the series. So I can change I to k, or just keep this. That would be the series of this fi x. And on the right hand side, I know this is just equal to the integral of the infinite sum. Okay, so this is actually the left hand side in the claim, and this is the same as this right hand side. Okay, so that's the proof. Okay, so that's just a simple kind of corollary of the Bipolar theorem. Now let's consider another corollary of that. So what it says is, suppose we have a sequence of sets ek. Suppose all of the EKs are measurable and also mutually disjoint. Okay, and let E to be the union of them. Okay, now remember that the EKs are disjoint and they're taking union of them. It's just the entire E. And suppose we have a function that is defined over E, and then that is non-negative, measurable. Then we can claim that the integral of E of f over E is just the same as taking the integral of f over each ek and sum up the integrals. Okay, and the proof is again very simple. You just need to check. Say I can define my fk to be f times the characteristic function of ek, and then we know that this we know that two things. One thing is that the sum of fk, k going to from 1 to positive infinity, is just the sum of this fc the chi ek, and we can pull out the f. It would be just the sum of chi ek. But this one here is just the chi of e, which is, it's just always equal to 1 because we're considering a function over as defined over e. So it's just equal to 1. So the series, the infinite sum of fk is just f itself. Then we can apply the theorem before. This integral of f is just equal to the integral of this. Right? And because of the theorem before, this is just equal to the integral sum of the integrals. Okay, so that's the corollary here. Okay, so this is actually a generalization of the countable additivity of measures, because let's say that if we take f to be constant 1, then the left-hand side here, if you take a constant 1, the left-hand side here is just the measure of E, right? This is just the measure of E. And on the right-hand side, this is just the measure of EK. This is the one here, just the measure of EK. So the corollary above just implies that the measure of E will be equal to the sum of the measure of EK. And this is actually the property of measures, or Lebesgue measures, which is countably additive. If you have countably many sets that are disjoint, then the union, the measure of their union, which is this, is equal to the sum of their measures. Right? That's the countable additivity of Lebesgue measures. Okay. Now let's consider an interesting example. Let's suppose we have a P subset of the interval 0 to 1. And every point of the interval is covered by or belongs to at least a k of those sets. Where this k apparently has to be less than or equal to p. If this is the case, then you look at the measures of these sets, then at least one of them has a measure bigger than or equal to p. Okay, so we just have subsets of the interval 0 to 1. So there are different types of subsets of this interval, and if every point is covered or belongs to at least k of this p sets, then at least one of these sets has a measure bigger than or equal to k over p. Okay, and the proof is pretty simple. They just look at the sum of their measures, or better, we assume those sets are all measurable sets. So we'll consider the sum of their measures, and then we know that each one of them, look at each EI, the measure of EI can be considered as the integral of the characteristic function of EI. Okay, in the whole set is 0 to 1, so I just take the characteristic function of that, and apparently I can exchange the sum and the integral. But this is the finite sum, and apparently it must be true. Now let's look at this one, the integral of this, or the sum of this. So this is just the sum of p characteristic functions, and we know that for each x, this characteristic function is 1 if it's inside EI. But as we said, that the x belongs to at least k of them. So that means here the sum is at least bigger than or equal to k, right? Because it's going to, the characteristic function will be equal to 1 for at least k of those k of these p functions. Okay, so that means this is bigger than or equal to the integral from 0 to 1, taking the integral of this over k, for k, and this is equal to just k itself, because k is a constant. And now we see that the sum of these ones is bigger than or equal to k, and then at least one of them must be bigger than or equal to k over p. The reason is if every one of them is less than k over p, then the sum of them must be less than k, and that is a contradiction to this one. Right? So that's why the mu of EI must be bigger than k, bigger than or equal to k over p for at least 1I. Okay. Okay, now let's consider a very important result of the analysis. It's called the Feto's lemma. Okay, so that's a very, it actually has a name, and it's very powerful. We saw this name earlier. It's Feto's lemma for sets, but the most widely known lemma is actually defined for general case, which is for integrals. But this integral version can imply the set version, as we can see. Okay, so what this lemma says is, the interesting about the Feto's lemma is that it doesn't require any much condition. It's really trivial condition, but we can get that conclusion. Okay, so that means it almost came for free. So what it says is that if we have a sequence of non-negative measurable functions, then the integral of their lower limit of the sequence. Let me write it out here. Squeeze a little bit into one line. Feto's lemma. Suppose we have a sequence of non-negative functions, then the integral of their lower limit, so there's the lower limit of the sequence, apparently for each point, or you ignore the all means this notation here, is less than or equal to the lower limit of the integrals. Okay, so as you can see, it didn't require anything, just a simple, just that the functions fk's are measurable functions, non-negative measurable functions, then we can have this. Okay, the limit, the first one is that we take the integral of the lower limit is less than or equal to the lower limit of the integrals. Okay. The proof is not difficult either. It's just based on the following fact. Let's define or denote the gk function to be the infimum of fkx or fjx for j bigger than or equal to k. Okay, so now you can see that the gk is non-decreasing, because if k increases, then we're taking the infimum over, so if k becomes k plus 1, say, then we're taking infimum for all the j bigger than or equal to k plus 1. That means we're taking infimum of fewer sets, so that means one fewer set, so that means this must be, we will potentially get a larger value. So that's why the gk must be non-decreasing. Well, if it's non-decreasing, then we can apply the Bipolar. It's non-decreasing and it is non-negative, so we can claim that the integral the integral of the limit gk is equal to the limit, the limit of the integrals right? On the left-hand side, we know that since gk is defined as the infimum here, so you know that the infimum, the lower limit is just can be defined as the limit of the infimum. So this is why inside integral, just look at the inside of integral, it's just the lower limit of fk. Okay, and that is what we needed for the left-hand side. On the other hand, this limit of the gk, recall that the gk is the infimum of this fj for j bigger than or equal to k, so that means the ek itself, gk itself must be less than or equal to fk, because fk is one of these sets for g bigger than or equal to k, right? So that's why this must be true. So that's why the gk, the integral of gk must be less than or equal to the integral of fk as well. Okay, so that's why you take the limit lim inf of gk is also less than or equal to the lim inf of fk. But right now we know the limit exists for gk, so the lim inf, the lower limit of the integral is just equal to this, and that's less than or equal to the lower limit of the integrals of fk. And that finishes the proof. Okay, it's a really simple result. We don't really need anything, but we can make this conclusion. Okay, a simple case that if all the fk's are less than or equal to, has an integral less than or equal to m, then if every one of this is bounded by some number m, then the lim inf is just bounded by m as well, and that means this is bounded by m, right? So the lower limit of fk, the integral of the lower limit of fk will be bounded by m if each one of them is, each integral is bounded by m. Okay, so that's a trivial special case. Okay, but what's more important here is that the Fato's lemma only gives us this less than or equal to. We don't really have this equation equality hold in general, and we can create many counterexamples to show that the strict less than could happen. For example, in the following function, this is actually one of the functions we saw earlier. So let's say we define the fkx to be, let me first write out the function and then show you what actually it is. Okay, so the function is actually this. Let's look at the set 0 to 1. The f1 is taking, sorry, I should write in a, should not use 1 here. Okay, so it's not really on proportion, but the first function is that this is the 1, and 2, and 3, 4, like this. So the first function is this. Second function is this, so 1/2, and the third function is 3 over 1 over 3. Okay, you can imagine what happens for 4 is just a 1 over 4. So the key here is that each one of them has an integral equal to 1, because you look at the rectangles, they all have the area 1, but they're converging to 0 almost everywhere, because you can see that the support of these functions is getting smaller and smaller, eventually approaching to 0. So fk actually goes to 0 almost everywhere. So with that, it goes to 0 almost everywhere. So that means that 0 is the limit. I call it f. Now let's see the integral of fk. We see that it's always equal to 1, right? For all the case. And the integral of f apparently is 0, because f is a 0 function. So that means the lower limit of fk actually is just the limit of fk, because fk actually converges. So this is just the integral of f. From 0 to 1, and we said this is equal to 0, right? And on the other hand, we know that's the integral of this, each of this fk is 1. So we take the limit of them will be also equal to 1 as well. So the limit of the integral of fk, apparently this is just it's also the lower limit, because the limit actually exists. Each one of them is equal to 1. This is also the lower limit. And apparently this is not equal, right? 1 is 0, the other side is 1. So the strict equality could happen in general. So we don't really have equality. So that's the best we can get. Okay, so the Losses theorem in this section is that suppose we have a function f, a non-negative measurable function f, defined over E, and the set E has a finite measure. And then let's say suppose we partition the range of this function f into those small pieces defined starting from the y0, and y0 is just y0 is just equal to 0, and then y1, y2, and the gap between each adjacent consecutive two numbers is less than delta. And then we can define the set ek, which is a set of points where the function value at that point it falls to be between yk and yk plus 1. Then we can make a claim that the function f is integrable. That means the integral is finite if and only if the infinite sum of yk times mu k is also finite. So what the meaning of this is, say suppose this E is just in R1. Okay, E is just in R1. Then we can partition the range so that This is the y0, this is the y1, y2, y3, y4, and the gap between every one of them, those gaps are less than delta. Okay, and then for each one of them, for example, take the y2 and y3 as example. If the function value falls between this, it's bigger than or equal to y2 and less than or equal to y3, then say for example the function like this, then this set here, this will be called E2. Okay, if the function value falls between y2 and y3, then the set is, the point belongs to the set E2, so on and so forth. And the claim is that if the function is integrable, if and only if you take the smallest value, which is y2 here, you take the value y2 and multiply it by E2, and apparently you have this for every case, so you have y1 mu e1 all the way like this, and then the function is integrable if and only if this infinite sum is finite. And that's not difficult to see for one side, because this is like a lower estimate of the function, the integral of the function, since the so for example y2 times the mu of e2 is just this area, right? And apparently it's smaller than this area here below this curve. So this will be a lower estimate or underestimate of this integral. So if this is finite, then this must be finite as well. The question is, if this is finite, can we imply that this is also finite? Okay, and that is because of the difference of them is always bounded by delta. And from there, it will be not hard to show this is true. Okay, so let's see how to prove them formally. Okay, so apparently we know that the function fk x is bigger than, so let's say we know that the integral of f over ek is less than or equal to yk plus 1 times mu ek, because over this set ek, the function value is less than or equal to yk plus 1, but it's also bigger than yk. So that's why we also have this side. Okay, and you know that this ek is a disjoint union, forms a disjoint union of the set E, of the entire set E. In the set where the function takes the infinite is has a measure 0, because the function f is finite almost everywhere. So we don't care about that side. So the union of ek will be just the E except for a measure 0 set. So we know that taking the sum of this of these three terms, we'll get sum will be less than or equal to the sum. I should say starting from 0, the integral of f over ek and this is just as we showed before, this is just the integral of f over the set E, because the ek is as we said, is a disjoint union of the set E. So it's just this, and that's less than or equal to the sum for k from 0 to infinity of the yk plus 1 mu ek. Okay, let me erase those. Okay, and apparently for each one of this ek, we know that this is not far from the yk itself. So yk plus 1 is not far from the yk, because it's just we just have this property, it's less than or equal to delta plus yk. So that's why this is just less than or equal to the sum of yk mu ek plus delta times the sum of mu ek. But since you know those ek's are destroyed, so I know that this part here is just the mu of e. Okay, so now show that the integral of f is bounded by, I call this set S, and it is bounded below by S, and it is bounded above by S plus the delta times mu e. But this is a finite number. It's a finite number here. So that means if integral of f is finite, then S is finite because of this set. If this is finite, then this S must be finite. On the other hand, if S is finite, and because this is finite, now I can show this is finite, and that means this is finite as well. So that means f is integrable. Okay, and moreover, we can see that if delta is approaching to 0, we can make this true for any delta, and delta approaching to 0, then this one will approach to 0. And by squeeze theorem, we know that the integral of this is just equal to S, which is the series here. Okay, so that's the proof for this theorem. Okay, so now we can consider the integral of general functions. Previously, we considered the non-negative functions. Extending them to general functions will be trivial because we can always separate a general function into its positive, into the difference of their positive and its negative. Okay. Okay, so here's the definition for integral of general functions. Suppose we have a measurable function f defined as a function over a measurable set E to the set of extended real numbers is measurable. And then if we can look at the positive and negative, you know that f can be written as f plus minus f minus, where f plus of x is equal to f if f(x) is bigger than or equal to 0, and it's 0 if f(x) is less than 0, right? And then similarly, f negative is defined as f negative fx, where f of x is less than or equal to 0. If it's 0, and it will be equal to 0 if f is greater than 0. Okay, so that's the f plus f minus. Okay, so if at least one of these two is measurable, or has a finite, at least one of them has a finite integral, then we can define the integral of f to be the difference of them. The reason why we require them to be both finite is because I know both of them will be non-negative. If both of them are positive infinity, then taking the difference of them is not defined, as we made our context at the very beginning of this chapter. But only if one of them is finite. So for example, if this is finite, this is infinite, then difference of them is negative infinity, and we can still say that the integral of f is negative infinity. Or otherwise, if this is a positive, this is a finite, then we can still say that the integral is positive infinity. But if both of them are finite, if this is a finite number, this is also a finite number, then taking the difference of them will be also a finite number. And only in this case, we call the function f integrable. Okay, so integrable if and only if this and this are both finite. Okay, and in this case, we also denote this f to be in the set of LE, where L means the Lebesgue integrable function over the set E. Okay, so this excludes a special case where, say, I have function f which is just equal to the x itself. So, for example, the f of x, f is defined as a mapping from R to R, or fx just equal to x, then f is not integrable because apparently this is both of these are actually even the integral is not defined because both of these are positive infinity. Okay, and even if it's just say similarly if fx is said to be the maximum of x 0, then this is still not integrable because the function function is just equal to x for from 0 to positive infinity, and this is still infinity. So this is not measurable either, not integrable either. So the integrable only if and only if both of those two functions are integrable. And if this is true, we know that the f can be written as f plus minus f minus, and the absolute value of f can be written as f plus plus f minus, right? But if both of them are integrable, then we know that integral, that means both of them have a finite integral, then the integral of this absolute value will be equal to the integral of f plus plus the integral of f minus, and this is also finite. Right? So that means the function f is integrable according to the definition here. Function f is integrable, then the both of these two integrals are finite, and that is also saying that the function, the absolute value of function f is also integrable. This is also integrable. Okay, so this f is integrable if and only if. In other words, f is integrable if and only if the absolute value of f is integrable. Okay, that means f belongs to this if and only if the absolute value of f belongs to this. Okay, so that's the definition for, that is one property that we can derive for integrable, the definition of integrable functions. Okay, and there are also other trivial examples. For example, if f is bounded by some, say, we know that absolute value of f is bounded by m, and the measure of the set E is finite, then apparently the integral of f over E will be bounded by m times the integral of 1, which is just the measure of E, and this will be finite. And because this f has a finite integral, that means f, absolute value of f is integrable, and that also means f itself, which could be positive or negative, could be taking both positive and negative values, is still integrable, right? Because this one is integrable. Okay, so these are really trivial results that we can claim due to the definition of integrable functions. And there are also a few other quite easy results with the list here. So, for example, if f is integrable then the absolute value of f is finite almost everywhere. And this is apparently is true is because the f can be always written as, so it's f plus minus f minus. So each one of them must be finite almost everywhere, right? Oh, I'm sorry. The integral of f is integrable. That means both of this f plus and f minus have a finite integral. So that means this must be finite, and also this must be finite as well. And both of them are non-negative functions. And we showed before that if function is non-negative, then and the integral is finite, then it must be this f plus must be finite almost everywhere. The reason is if it's not finite almost everywhere, then it will be equal to positive infinity over a set with positive measure. And in that case, say if it's taking the value positive infinity over a set, say E delta, but this E delta is not a measurable set. It's not a measure zero set. So that means this one is still positive. Then the product of these two will be positive, right? Will be positive. And your integral of f must be at least this large, right? Because this is taking integral of f plus over the entire E, and it's taking positive infinity over this E delta, then this integral must be bigger than that, and that's already infinity. And that is a contradiction. So this cannot be true. So that the f plus must be finite almost everywhere. And similarly, f minus, if its integral is finite, then the f minus must be finite almost everywhere as well. So the difference of these two will be finite almost everywhere. Okay. The second is that if f is 0 almost everywhere on E, then the integral of f will be just equal to 0. Okay, and this is apparently true because again we can separate this E, partition this E into two sets. One set has is where the function f takes the value 0. The other set, which is complement, is where f can take non-zero value. But that set is just the complement is just a measure 0 set. So we take the sum of them is still a measure is still 0. So it's just equal to the integral of E1 of f plus the integral of E2, where E1 is defined to be the set where f is equal to 0, and the E2 is just the E minus E1, but the mu of E2 is equal to 0. So that's why this is just equal to 0. This set over here, this is equal to 0. Over here is also equal to 0 because E2 has a measure 0. Okay, so that's the second one. It's pretty simple to show. Also, if f is measurable and the G is positive, we'll say that it's actually positive, it's integrable in the f, absolute value of f is less than equal to G, so G is then negative here, then the f must be Yao-E. Okay, and that's apparently true as well because if we can just look at the absolute value of f because this is bigger than or equal to 0. So if we take the integral of f, that will be less than or equal to the integral of g. But integral of g, that is finite number because g is integrable. On the other side, it's greater than or equal to 0. So that means the integral of the absolute value of f is integrable, and we know that this is integrable if and only if f itself is integrable. Okay, so that's why this is true. And finally, if f is measurable, is integrable over the entire Rn, then just try this. Then you look at the integral of f over the set outside of the ball centered at 0 origin, and with the radius f. If you look at this integral, this will convert to 0 as k goes to positive infinity. And that means you're taking the integral of f outside of this ball, which is growing to the entire Rn. You will see that the integral of this will be equal converging to 0 as the ball gets larger and larger. Okay? And to prove this also is really simple. We can consider the f again into two parts, f plus and f minus. Say let's look at the f plus. Then we know that the f plus, when we multiply this f plus by the characteristic function of this b0k, then we know that we multiply these two functions together, we call it fk, let's say. I know this is a non-negative function. Fk is non-negative, it's decreasing. For k gets larger, getting larger and larger. And for f1, it is integral of f plus over the area outside of the unit ball. But we don't even know that the f plus over the Rn is finite because it's integrable. So the f plus is has a finite integral, and it must be bigger than or equal to the integral of this minus the b01 of f plus. And this is just equal to the integral of f1 over e over Rn. Okay, so the first one has a finite measure, and the fk is decreasing. So according to the remark we made after the Bipolar, we know that the limit of fk over Rn will be equal to the limit of the integral over Rn. Right? But on this side, this is just the limit of this Rn minus the ball 0k, because fk is this one. It's f plus times the characteristic function. So that's just this. And on the left hand side, the limit of this, because the k is getting larger and larger, so this one will convert to 0 point-wise. So that's why this one is going to 0. So that's why this is just equal to the integral of 0, and that is 0. Okay, so we can show that for f plus, this limit goes to 0. And then similarly, you can show the f minus, take an integral of f minus over the same side, the limit is also going to 0. So that's why this the difference will be also having a limit going to 0. And that completes the proof. Okay. There are also several other very trivial results. For example, the integral is linear for general measurable functions, and I will not prove this anymore. You can see that you should again just separate them into plus and minus. You can show that this is true. And similarly, the integral, so they're all defined over E. You take the integral of the sum. This is the same as taking the sum of their integrals. Okay. Now let's look at another example. Say I have a function f that is a mapping from the interval 0 to 1 to R, and it's measurable. Now suppose that the integral of fx times log of 1 plus fx. Suppose this one is finite. Then the f itself must be integrable over the interval. Okay, so looks like this came from nowhere, but actually the idea here is that we can partition the interval 0 to 1 into two parts if the function f is integrable on both of these two sets. Then the function will be integrable. Okay, so the proof is, let's consider for example, the E1. So let's say the E1 is a set of points where the f is bigger than or equal to E minus 1. And over this set E1, we know that, so if x belongs to E1, then the 1 plus f of x will be bigger than or equal to E, right? And the log of them will be bigger than or equal to 1. So in this case, the f of x times the log of 1 plus f of x will be bigger than or equal to f of x, absolute value of f of x. Okay, and then we can take E2 to be the complement of E1. So if x belongs to E2, then apparently the absolute value of f at x is less than E minus 1. So now we can partition the integral of absolute value of f into two parts. One part is over E1 of f plus the integral of absolute of f over E2. And over the E1, we said that this is less than or equal to the integral of this f times the log of 1 plus the absolute value of f. Right? According to our the first case, we know that this one is smaller than or equal to this. And on the E2, we know that this is just less than or equal to E minus 1. And for the first one, we know that since this one is bigger than or equal to 0. This is also bigger than or equal to 0. So that's why you take the integral of some non-negative value over a smaller set, it will be less than or equal to the integral of this over the entire set. So this is why this is just less than or equal to the integral of this. And this one is also the same. It's just less than or equal to the integral of E minus 1 because this is a positive number. And both of them are finite. Okay, so that means the integral of f, absolute value of f is finite, and that means absolute value of f is integrable, and that also means f itself is integrable.